All right, kids, we're going to jump into it. A geometric sequence is formed by multiplying a constant to the previous term. So we're multiplying to get to the next term every time. That's called the common ratio, but the ratio can't be 1 or we wouldn't change anything. This means that every geometric sequence will be exponential. We're going to determine if the sequences that we're going to look at are exponential, so they're geometric, arithmetic, which would be linear, or neither. If they are one of the two, arithmetic or geometric, we're going to find the common ratio or common difference. So when we have a list of numbers or a sequence here, we can check to see if it's geometric. We're looking to see, did they multiply to get the next number by taking some value and dividing by the value before it. Okay, so 0.2 divided by 1, 0.04 divided by 0.02. And in all these cases, they're the same. It is 0. Oh, no, not that. Hold on. Sorry, kids, but that couldn't stand. Anyway, they're all 0.2. And that means that is our common ratio. So we can find a common ratio just by taking any term and dividing by the term before it. And that's equal to r, if there is an r. If not, then they'll be different. All right, so the next one, we have 180, 90, 60, 15. If I look here, I'm dividing by 2 or multiplying by a half, or I can try to think of like the common ratio here, right? So if I tried 90 divided by 180, I get 1/2. And if I do 60 divided by 90, I get 2/3. And those are not the same. So this is neither. And we could find a pattern, right? You could probably see what's happening and make a guess as to what the next value is going to be, but it's not geometric, so we're not going to bother with it. And then lastly, maybe this is the last one, but we're going to go, I'm not, when it's gross like this, I don't think multiplication right away, but we can always check it if we have to. But I can see that I'm subtracting 7 and subtracting 7 and subtracting 7. So my common difference is -7. And we can even go back and say, oh, well, I know that a sub n equals -7n plus 107 because this is that dn plus a sub 0 term, even though there isn't really one, right? That we did last time. And here I have, let's see. I could try addition, right? Plus 18, but this isn't plus 18. All right. I guess we can try a common ratio. So 72 divided by 54 is 4/3. 96 divided by 72 is 4/3. 128 divided by 90. Ooh, that's supposed to be an 8. 96 is 4/3. And kids, don't put it past your evil math teachers to wait until the end or somewhere else that it's not obvious to get to see if you really found the common ratio. But we did. It's geometric, and r is 4/3. Okay. This is off of our IB formula chart. So they use U's, not A's. So this is U sub 1 and U sub 2 and U sub 3 for the term numbers. And they have a couple different variations. If you notice, if they factor out a -1, they just, from the top and the bottom, they're just switching the signs inside the parentheses. That's all it is, right? This is typically the form that we see it in. So that's the one I'm going to use. But I don't know. They wanted to show you factoring by -1, I guess. So let's say we have a sequence first. We're not doing sums yet. We're just going to focus up here. But we have a sequence, and we have something like something basic, right? So maybe we start with 5, 10, 20, 40, 80, 160, right? And hopefully everyone can recognize I'm multiplying by 2 every time, right? So this is times 2. So that's our common ratio. So r equals 2. Then I know my first term is 5, right? So when we're building this formula, we say, okay, well, u sub n, any term, is equal to the first term times our common ratio to the n minus 1. And the reason we put minus 1 here is so if I plug in 1, I have 2 to the 0, which is just 1, and I actually get back my first term. Now, you taggy kids that are out there could also write an expression where we have u sub n equals, and then you could go back a term like 5 halves times 2 to the n. And if I plug in 1, now the 2's cancel and we get 5 anyway, right? There's lots of translations that we could make up and down the number line to get an expression that would work. But I'm going to ask that most of the time we use the formula and we write it in terms of n sub 1. So we all have something that's similar that we're looking at. I won't count this one wrong, though. But if you get too creative, I might not recognize it and count it wrong. Not that it matters in the pass-fail class right now, but in the long run, just be careful how out of the box you're starting to think. Okay, so we're going to find the recursive and explicit formula. We didn't talk about explicit formula here with my last example. So let me talk about, recursive formula. We didn't talk about recursive formula, so I'll talk about that real quick. Remember, recursive formula has two parts. We always want to define a sub n, or I'll put u sub n, or u sub 1, I mean. U sub 1 equals 5, right? There's our first term. And then the next term is equal to the term before it, u sub n minus 1, times 2. And there you go. That's it. That's all we're doing. Okay. So we're going to find the recursive and explicit formula for the following sequence. First, we probably should check to see if it's geometric. If I'm going to multiply to get to the next term, times 2 up here. Ooh, that's gross. So instead of trying to guess at what it is, we can just take the term, 6/7, and divide by the term before it, 3/4, which is the same as 6/7 times negative 4/3. And we get a little bit of action here. And I get negative 8/7. Well, if I go from 6/7 to negative 48/49, 6 times negative 8 is 48. Negative 48. 7 times 7 is 49. 49 times 7 is 343. Hopefully you recognize that's 7 cubed. And then 48 times negative 8. Yep. Okay, so we got that. We know it's geometric. We tested the ratio. We feel good about that. And then our recursive formula, remember recursive, here's our recursive. We're going to do the first term, u sub 1, or a, or whatever you want, equals negative 3/4. U sub n equals u sub n minus 1 times negative 8/7. Okay. And then our explicit, we had that, and if you need to go back and write down the formula, you should have done that, I guess, but pull us back a little bit and look at that formula. U sub n equals, I'll just write it here for you. Oh, man. U sub 1 times r to the n minus 1, right? So u sub n here equals negative 3/4 times negative 8/7 to the n minus 1. And we, for the record, because we have a negative in the exponential for the base, it's not an exponential function, but it is an exponential relation. Because if we graph this, when we defined exponential function, we said the base had to be greater than 1, I think. But if we graph this, it's going to oscillate back and forth over the x-axis as the terms go positive and negative for the y values. All right. Yep. Okay. Oh, I didn't do the 20th term. Dang it. Well, there it is. Now we want to know the eighth term of geometric sequence if we know this. Now this is similar. I don't know the first or the second. I know the third term is 36. I don't know the fourth. I know the fifth term is 324. And then we want to know 6, 7. We want to know the eighth term. Well, really, we need an explicit formula. We can just plug that in, right? The idea here is that I'm multiplying by the ratio, and then I'm multiplying by the ratio again. So I know that 36 times r's twice, right? It's regardless of how many, this is how many r's it took to get there, equals 324. Then I'm going to do divide by 36 on both sides. 324 divided by 36 is 9. So r squared equals 9. And r could be plus or minus 9. It could be. So I have to have two different solutions depending on where I end up, right? Because the eighth term is an even term. It could be positive or negative. Because all the even terms could be switching signs, right? So when I write my formula, I have a sub, it's hard for me to switch. A sub n equals, I got to go back. If I divide 36 by 9, I get 4. So a sub n equals 4, because this would be 4 times 3 times 3, right? Or negative 3 times negative 3. So I get 4 times plus or minus 3 to the n minus 1. And we're going to have to do it twice just to see what we get. Okay, so when I put that in there, 4 times 3 to the 7th, I get 8748. Or if it was the negative 3, then it would be negative 8748. And that's how I do this problem. Sweet. So I had to go back and find this term. I had to find the common ratio. Then I had to go find the first term so I could use the formula. We could have also translated this and used a sub 3, which may have been fun to do. Okay. 33rd term of geometric sequence. Now we have a sub 7 and a sub 19. I'll give you a minute. I want you to try that out. We want to know the 33rd term. We need to find the ratio first, and then we need to find the first term, unless you want to write it in terms of a sub 7 if you want to challenge. All right, I'll give you a minute. Pause the video. Hopefully you did this. I always imagine that like there's some kid, some of my really quiet, hardworking kids that actually did it, and I really hope that's true. But I imagine other students that don't really follow directions very well. Thinking about you, Eric, who's not even watching this video. Let's not kid ourselves. He didn't pause the video. If anything, he fast forwarded. So he's watching this on like 1.5 or 2x speed. And anyway, so we have a sub 1, 2, 3, 4, 5, 6, 7. A sub 7 is 0.001. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Now, I do this really just for the visual, right? How many R's am I multiplying? Well, if I'm going from 7 to 19, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's the same thing as when we're trying, well, it's not the same thing. So we can look at the subscripts, right? To go from 7 to 19, I'm multiplying 12 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 to get to that term, right? So this is going to look like 0.001 times r to the 12th equals 4.096. So then I've got to divide by 0.001, which is going to move the decimals, right? And to take the 12th power, that's what I'm doing really here. Not 12th power, take the 12th root. So you can do 12th root on if you hit math on the calculator key, and then choice 5 gives you any root you want, in case you didn't remember that. So I have r to the 12th equals 4096, and then the r equals the 12th root, and because it's even, it could be either one. This is the 12th root, and we get 2. Oh, this is 4. Oh, man. This is going to be awful. All right, let me go just do that. 4096 equals plus or minus 2. So if I want the 33rd term, now because the 33rd term is also odd, I don't have to worry about the sign change. So I can only use the positive term here. And so if I'm going to divide by 2 as I go back, I'm going to divide by 2, 4, 6, 8, 10, 12. Well, that's not true. 2, 4, 8, right? So divide by 2, 1, 2, 3, 4, 5, 6. So divide by 2 to the 6th, 0.001, 2 to the 6th. Ooh, that's really, really small. And then I'm going to multiply that times 2 to the 32nd. So I got 0.000015625 times 2 to the 32. Right? Because this is n minus 1. And I got 67108.864. If I did it right, let's see what the PowerPoint says. Oh, man. Oh, that's great. Okay. So now a real quick thing on geometric means. It's between these two terms is the square root of the product. Remember that if we do geometric mean, you're taking the square root of the product of the two numbers. Like arithmetic mean, you add them up and divide by how many. Now, remember this. This is the math part I wanted to talk to you about this, right? Here's A, here's B. You can certainly multiply 4 times 25. That's not too bad. But remember that if I do AB, that's the same as A times B. And since both of these happen to be perfect squares because your math teacher that wrote this question couldn't get more creative, we could have just done 2/3 times 5/6, and that's a little bit easier for me to do in my head. And I should have canceled that. Now I regret my life's choices, kids. 5/9.